change. There's yours. Thank you. Lin Haskins.
I'm going to set a little timer going because I do want to make sure that there's enough time at the end for a bit of a discussion. So I think this is a particularly good subject for that. Okay, so I'm just going to dive straight in. Climate change. It's already very much here, and it's already giving us fascinating data. Really fascinating data. I'm an unapologetic enthusiast about this. It's really just a brilliant time to be a climate physicist. So we're already seeing all these changes around the world. Lots of droughts, more intense hurricanes, more hurricanes, hurricanes out of season. We're seeing flood events. Sometimes where you wouldn't expect them, and others just far more intense than you'd expect. You might be a little bit more surprised about the fourth picture there. Basically, these first three, they all lead to agricultural disruption. Agricultural disruption leads to food shortages. Those lead to civil unrest. And there's a strong relationship between that and toppling weak governments. You get that, you get this, you get large-scale migration, forced migration. Okay. And on to everyone's favourite part of climate change, where we'll talk about the most, global warming. We've covered little fun facts. Of the 17 warmest average global years since 1880, 15 have been since 2000. One of the two that wasn't was 1998. To put that in perspective, the last coldest year on record was 1911. 2016, off to a fabulous start. Really just hitting the records right from the beginning. So January, new hottest January. The last coldest January, last record-breaking cold January was 93. So way back, good trend. Very good statistics on that trend. And as of March the 3rd, new exciting landmark achieved in climate change. For the first time, we had a global average temperature 2 degrees above average. So, pat on the back. One thing you will notice here is that it's not systematic. Different areas warm at different rates. In the middle of a continent, you have faster warming than in maritime climates. That's standard physics, and it does of course mean that landlocked areas, lots of people, the agricultural have a greater rate of change to try to keep up with. Lifestyles and communities will have to change faster. You will also notice that the scale bar isn't only positive, there's also some negative. We've had some areas get colder. You'll notice also that that magnitude is smaller, the spatial area much smaller. Climate change deniers love this. They get really excited and try and focus in on a small area or a small amount of time. But this light blue patch over the North Atlantic, referred to as the warming hole, and that it's a gap in the warming trend, is my personal favourite area of this system. Big fan, big fan. And I just want to explain to you quickly why this area has atmospheric cooling. Alright, so, nice little schematic for you. I drew it myself, in case you can't tell. Okay, so we have the Atlantic. South Atlantic, North Atlantic, Arctic. At low latitudes, we've got a lot of sun coming in per area. It warms and expands the water in the surface of the ocean. expands, it's more buoyant. It travels happily up to the north. As it travels north, it gets rained on a bit, making it a bit fresher, a bit more buoyant. But the interaction with the overlying atmosphere cools it, and that cooling gets it dense enough to sink down through the water column and return south at depth. That's the overturning, and that's what I study. Basically, when you get climate change and global warming, we have more rain in the North Atlantic, and we have ice melt, and a few other little things like that come together to mean that the water at high latitudes here stays buoyant. It's getting warmed more, it's getting rained on more, it's not sinking down as fast. So this whole overturning slows down. The IPCC report, which is the Intergovernmental Panel on Climate Change, can be taken as like a climate scientist consensus, is suggesting that by the end of the 21st century, this transport is going to have slowed down by 25%. But how does that make the atmosphere cold? This is what transports heat northward. This is why London is milder than Moscow. If this transport slows down, we don't have so much warmth being brought north, and so that area of atmosphere cools down. Simple as that. This is a fun little bit of colour. Nice pretty picture for you from observational data. This is over a 35-year observational record, showing the anomaly for times where the transport was relatively slow. Just to give you an idea of what I'm talking about here, best, most relevant pretty picture I have in my collection. So, things to notice. In this condition, when you've got the slower transport, you see the red next to the American coast? It's a bit warmer there, the water's warmer. When the water's warmer, it warms the atmosphere above it. So you have a warmer air mass next to America there. The really fun thing about that, which is it's going to be a global party with this bit, with climate change, it's that as air warms, it can hold more moisture. For every 1 degree of warming, it holds 7% more water at maximum capacity. So what you have is more water held in the atmosphere there. And as that travels inland and it meets the colder air mass, you get snow come out. A lot of snow, as may have been noticed. And as the atmosphere warms further, that will instead be rain and flooding. Now, if you follow that line, the average date at the moment, it's a bit further south. And we get storms all over Europe with that. When the transport slows down, the way the Gulf Stream comes across the Atlantic shifts northward. And you get a stronger sea surface temperature gradient in that region. So the warm water is warmer than it was before, the cold water colder than it was before. And where they meet, the impact on the atmosphere from the different degrees of warming and expanding causes a lot of instability in the air mass. This energizes and anchors the storm tracks over the North Atlantic. And that means that Northern Europe gets all of the storms belted at it. And they're more intense storms. So you'll want infrastructure in place for that. You might think that Southern Europe's getting off light at this point. It's not, unfortunately. They get fewer storms than usual, which means they get drier, they get less agricultural production in most of the studies. Well, all of the studies. But I'm a computer modeler. That's the way that I approach these questions. I'm not just looking at what we've got now and the data we've got now. I want to know what's going to come next, because what we're talking about here is huge. I mean, the lives that depend on knowing what's coming and having the infrastructure in place we want to know what we're talking about. And this may look a little bit upsetting to the non-mathematically minded and everyone else as well. But this is pretty simple. This is just a box model. You've got 4 ocean boxes, 2 atmospheric boxes. And you're looking at the way that energy is transmitted between the boxes. Lovely. And these are great, because you've got a conceptual idea in your head and you want to put down some maths to see what mechanisms, what feedbacks might be in place. But naturally, you can't tell much about the world we live in from just looking at that. So instead, we use computer models, which can do far more than any of us can. So this is a 6-box model. I use a relatively coarse resolution model at the moment, which has over 150,000 boxes. And this has just got a couple of variables. Mine's got hundreds, far more than I could ever calculate on paper. And that's not just salinity and velocity in the ocean. I'm looking at all information about the clouds, the ozone, soil moisture, the height of vegetation over land, all being included in this. Later on, I'll use a higher resolution model run on the supercomputer at the Met Office to do more targeted analysis. And at that point, it's just such beautiful computers, really amazing models. And it's not the real world. I cannot stress this enough. I don't think I'm looking at the real world. I'm looking at a simulation. The model I use is incredibly impressive. I'm going to say that. But to make the maths work, there's an artificial island at the North Pole. And to make sure the ocean transports are as representative as we want them, we may have removed Iceland. So I hope nobody misses that. There's a couple of minor little tweaks in there. And we know when we look at model data and we compare it to the observational data, it's going to be different. It's going to be. And that tells us fascinating things about the model that we're working with. And it tells us what dynamics in the actual ocean we failed to capture. On the other hand, at the start of the model, the temperature and salinity across the ocean is steady everywhere. The temperature in the atmosphere is steady everywhere. You let that run 1,000, 2,000 years in the simulation. At the end of that, we have the Gulf Stream, we have the El Nino, we have the NAO, we have the jet, we just have so many things beautifully captured, because if you put the equations in, you get the world. So what we do get is incredibly impressive. Again, though I do say so myself. So what do I do with that? Back to this. Big fan. So, with climate change, there's a risk of certain tipping points. These are kind of your wild cards in the Earth system. They make it all much more exciting. One is that with a certain amount of increased rain, increased ice melt, if a chunk of the Greenland ice sheet comes off and melts nice and quickly, that could be really exciting data-wise. A couple of things like that. You can have sufficiently buoyant water in the North Atlantic that transport doesn't just slow down, it stops. And so in my work, I'm looking at the timescales of how quickly the transport can stop, what mechanisms are involved in that, and when you start to see those steps being fast in the real world, how much time and what will it take to stop the collapse from happening and being permanent on human timescales? So there have been various studies looking at what will happen if it goes horribly wrong. And this, by one of my supervisors, no bias there, looks at what happens within a decade of an AMOC collapse. And 1.7 degrees of warming across the northern hemisphere of cooling across the northern hemisphere, sorry. It might sound like that's going to be a healthy balance, but it's not. It's going to be really surprising. Natural systems don't like big surprises like this. And more excitingly, for northern Europe, within a decade, temperature drops of 8 degrees or so. Approximately 5 degrees in Southampton, for those more personally concerned. And all sorts of changes in rainfall. Agricultural surprises. And of course, because you've got to have a balanced system in terms of heat energy, we got warming in the southern hemisphere, balancing that. Hope you don't mind any ice there, Martin. So yeah, there's some really exciting things coming, and really good reasons to make sure it doesn't come. Plan A is, of course, emissions cuts. That is the sensible plan. Not forcing us far enough that this is a problem. Forcing us so far that it becomes a problem, but then going, I don't like problems, and changing it. These are all sensible ideas. Plan B is rapidly approaching. Plan B is geoengineering. Best, worst idea ever. Absolutely love this stuff. For academic reasons, not ethical ones. Important to say that. So, in order to actually be able to change the radiative forcing quickly enough that you'd be able to respond, best option, solar radiation management. And one of the approaches to this includes one of my favorite terms in modern science, space mirrors. Not even joking. Firing thousands of little mirrors up into space to deflect light from the sun. Genuinely being considered. Pretty sure The Simpsons did a mockery of that a while ago. I stand by their analysis. So, a slightly more sensible approach, and you may be surprised that I just said that, is basically trying to simulate a giant volcanic eruption, because those never end bad for people. Because, I mean, you have a volcanic eruption, you have the sulfate aerosols going up into the atmosphere, and then you get acid rain. But if you have a big enough volcanic eruption, they go up higher, and they stay there. They reduce the amount of light making it down here, which would slow down warming. And there were various ideas as to how we could get the aerosols up there that would totally not be easily turning into an acid rain-related mishap. Totally not. And the other issues are the other impacts of this. One is that you would actually have more cooling at the equator than at the poles. So again, ice caps, take your photos while you can. Then there's the fact that you're not actually changing climate change, you're just turning temperature down a bit. That doesn't change the impacts you're having on atmospheric circulation. It doesn't slow down ocean acidification, anything like that. So you have giant droughts across areas like Central Africa and Asia. One of the most recent studies on this, published a month or two ago, suggested that alone, just the drought issue related to this idea, could endanger the food production for 1 billion people on the planet. So let's make sure this doesn't become Plan A. There's a couple of other things with this, but I'll give you two more examples very quickly of other geoengineering plans. There's ion fertilization of the ocean. Find an area with lots of nutrients, not much life, likely limited by a micronutrient. Throw in a load of bioavailable iron. Biological boom. You want that those bodies basically just sink down, trap the carbon in them into the ground. Doesn't work. It all gets remineralized in the water, turned around. It's been shown again and again that it doesn't work. There are still wealthy people going around throwing iron in, calling themselves philanthropists. Technically illegal. Not least because it can create algal blooms that, you know, oil gets filtered through the food stream and it gives shellfish eaters mercury poisoning. Not great. And the other popular one is carbon capture. Kind of a nice idea. If you could scale it up big enough, because I mean it's basically giant fans trying to get all the carbon out. It works. Not necessarily on a global scale, not fast enough, not being invented fast enough. And the industries currently financing it are more oil and gas. And it's actually just for kicks. It's turned around from being how can we get CO2 out of the atmosphere to how can we capture that released carbon dioxide and get it back into the transport industry. So, oh yeah, free market economics has hit that one hard. And it's really driving the research. Just gonna happen. So yeah, emissions reductions before we start seeing the collapse would be the ideal, but I think we're going to see something far more exciting than that. Questions, queries, and comments?
Thank you very much, Lynn. I'm conscious of how much we're running over and also that people probably want a toilet break for our last talk, so I'm going to limit it to 2 questions. Yes.
That geoengineering one with the volcano sounded like the Matrix to me. But my question is, I don't know if you know about this. I'm a little bit confused about sea level rises and how they predict. Is it more a kind of ice caps or ice melting on the planet, or is it the oceans expanding because they're hot?
It's both, and it's also gravity issues. Yeah, that's a surprise. Nobody thinks of that one. So you've got thermal expansion, global impact. The ice caps is really about tipping points. Greenland goes, we should get the collapse I'm dreaming of. It's the sort of 60, 70 meter sea rise would be related to Antarctica, and that's at sort of like 2,000 parts per million CO2. We're currently at 404, I think. So that's a little way off in the future. The gravity issue is that, so for example, you've got the Greenland ice sheet. As that melts, it changes the local gravity fields. So the areas with the greatest sea level rise as a result of that are actually the further point from Greenland, because the water currently attracted towards that mass shifts away when the gravity leaves, and that shift can lead to a local sea level fall. And of course the local impact actually on Greenland itself of not having the weight of the ice on top leads that landmass to rise up with pressure, pushing it down. There's a lot going on with that question.
We have one last question. Yeah.
I've got 2 I'm talking about. If we talk about global warming because the ozone layer is getting thinner, is that right?
No, they're 2 separate things that we're doing to the planet.
Well, my question is going to be, why can't we put ozone back on? It's just oxygen, isn't it? Or derivative.
Actually, sending sulfate aerosols into the upper atmosphere would actually help that issue in that it would give surface for building ozone layer. It's just that generally speaking, everything that we could potentially do to fix the ozone layer issue kind of has bigger side effects possible. So it's more we could tamper, but it's probably best if we leave the system alone for a while. Because in theory, it'll sort itself out given time. And if we try to sort it out faster, we could get some very nasty surprises.
Okay, thank you very much for our amazing speaker, Lynn, again.